What challenges arise in serving large language models efficiently?
Challenges in serving large language models, LLMs, efficiently arise due to the autoregressive nature of LLMs, which necessitates loading the entire key value, KV, cache, and model parameters into GPU SRAM for every token generated, leading to low computational core utilization. The memory footprint of the KV cache, growing linearly with sequence length, becomes a bottleneck for long sequence generation. Existing methodologies, such as KV cache eviction strategies, struggle with potential information loss, including hallucination and contextual incoherency, particularly in long contexts. Speculative decoding, which accelerates LLM inference by using a lightweight draft model to predict tokens, faces challenges in training draft models to match the context length of target LLMs and maintaining high speculating performance with long sequences. The need for training-free, high acceptance rate, and low-cost drafting in speculative decoding poses technical challenges in achieving efficient acceleration for long sequence generation. These challenges hinder boosting speed without sacrificing model performance, as illustrated in the provided framework.
How does speculative decoding accelerate language model inference while maintaining output distribution?
Speculative decoding accelerates language model (LM) inference by leveraging the observation that generating one token takes the same time as processing multiple tokens in parallel. This method allows for faster inference by predicting the next few tokens using a lightweight draft model before verifying them with the target LM in parallel. By doing so, speculative decoding optimizes the utilization of computational resources, boosting the speed of LM inference without sacrificing the accuracy of the model's output distribution. The hierarchical speculation system introduced in TRIFORCE further enhances efficiency by addressing the bottlenecks associated with both model weights and key value, KV cache. The system employs a secondary lightweight model with a streaming LLM cache for initial speculations, followed by self-verification with the target model using a retrieval-based draft cache. This hierarchical approach reduces drafting latency, accelerating the overall inference process while ensuring the preservation of the original output distribution, as demonstrated in the standard speculative decoding algorithm.
What are the key observations that pave the way for designing TRIFORCE system for serving LLMs with long contexts?
The key observations that pave the way for designing the TRIFORCE system for serving LLMs with long contexts are as follows. 1. Hierarchical speculation for dual memory bottlenecks. Recognizing the memory bottlenecks of model weights and KV cache, with the latter becoming more dominant as context length increases, inspired the use of hierarchical speculation to address these bottlenecks sequentially using different draft models. 2. Leveraging attention sparsity for speculative decoding, identifying significant redundancy within the KV cache, where a small portion is adequate for a high acceptance rate, led to using partial KV cache as a draft cache for self-speculation, ensuring efficient inference. 3. Exploiting contextual locality for drafting efficiency. Discovering that information from long context tokens needed by adjacent tokens tends to be similar, suggested that a specific segment of the cache can be reused effectively across multiple decoding steps, enhancing drafting efficiency and reducing overhead. These observations guided the development of TRIFORCE, a scalable and robust speculative decoding system that integrates retrieval-based drafting and hierarchical speculation, optimized for both on-chip and offloading scenarios, to accelerate LLM inference while maintaining model output precision.
Can you explain the hierarchical speculation approach introduced in TRIFORCE?
The hierarchical speculation approach, introduced in TRIFORCE, leverages insights from the dual memory bottlenecks of model weights and KV cache to enhance the efficiency of serving LLMs with long contexts. The system utilizes a two-layer hierarchy to address these bottlenecks sequentially using different draft models. In the first layer, a smaller, faster draft model with a streaming LLM cache is employed to speculate the target model, with a partial but high-quality global context retrieved from the KV cache. This step aims to tackle the bottleneck caused by model weights. In the second layer, the target model self-speculates using the retrieval cache, which serves as a draft model with full KV cache, to overcome the bottleneck associated with the KV cache. This hierarchical speculation algorithm effectively reduces drafting latency, accelerating the overall inference process while ensuring the preservation of the model's output distribution. The correctness of the final speculation phase, which is identical to the standard speculative decoding algorithm, is maintained to guarantee the precision of the model's output.
What are the main empirical results and findings achieved with TRIFORCE system?
The main empirical results and findings achieved with the TRIFORCE system include significant speedups in long sequence generation for LLMs. Specifically, TRIFORCE achieved up to a 2.31 times speedup for Llama 2-7B 128K on a single A100 GPU and a remarkable 7.78 times speedup on two RTX 4090 GPUs in offloading settings, with a latency as low as 0.108 seconds per token. TRIFORCE was also able to efficiently serve a Llama 2-13B with 128K contexts at a speed of 0.226 seconds per token, which was 7.94 times faster on the optimized offloading system. Additionally, TRIFORCE demonstrated a 1.9 times speedup for large batch inference efficiency, outperforming small models with streaming LLM cache across all configurations. The system showed exceptional scalability, with a theoretical upper bound of 13.1 times speedup, showcasing its potential for dealing with long contexts. TRIFORCE maintained a high acceptance rate above 0.9 even at a temperature of 1.0, highlighting its robustness. The system's hierarchical speculation approach effectively addressed the dual memory bottlenecks associated with model weights and KV cache, leading to improved overall speed up. The integration of TRIFORCE with tree-based speculative decoding methods showed promise in further enhancing speedup by utilizing additional speculation budgets.
What are the implications of the KV cache quantization methods discussed in the paper?
The implications of the KV cache quantization methods discussed in the paper are focused on enhancing the efficiency of inference for long sequence generation while maintaining generation quality and reducing memory consumption. These methods aim to compress the bit width of KV cache activations, which is orthogonal to the approach presented in the paper. The KV cache quantization methods provide an alternative strategy to optimize memory usage and computational efficiency in serving large language models with long contexts. By quantizing the KV cache activations, these methods offer a way to reduce the memory footprint of the cache while still preserving essential information for text generation. However, it is important to note that the paper's approach, TRIFORCE, does not directly utilize KV cache quantization, but instead focuses on retrieval, based drafting and hierarchical speculation to address the bottlenecks associated with model weights and KV cache for accelerating inference of long context language models.